we can fix it. Yeah, I'm Joseph. I work for a company called Modulai. We just moved in at SUP 46, and we thought it cool to celebrate this occasion with what we like the most, machine learning. And we're a machine learning lab, so we help companies build awesome machine learning products. That's what we do right now. We have been doing this since March, April, 4 people. We're all 3 of us here, and Eric, who is the 4th part of the team, is in the US on the project. And these, basically, it's going to be a potentially big session, because it's based on 2 talks I have given at the machine learning meetup in Gothenburg. But we see how it goes. Depends also how much we discuss and you come with questions and so on. So the reason for this research is based completely on official data. I mean, data that we just got from the internet. So it's not related to a customer project. But the reason for the research is that we had a recommender project in the spring and did some research into state-of-the-art methods. So that's basically the backstory. And the talk will be based on 2 methods. One classical method, so it's not a deep method, but fairly state-of-the-art anyway for smaller data sets. And it's a paper called Metadata Embeddings for User and Item Cold Start by, I don't know how to pronounce his name though, Maciel Kula, from a UK company called Lyst. They do online shopping for clothes, I think. And he has written a really, really nice Python package for doing recommenders called LightFM. And it's based on a slightly older method called Factorization Machines by a German academic called Rendel. And he has, simplified the model a little bit and made it more implementable and usable. So that's the first part. I would call it the linear model, because it's basically linear. And then we go into the second part, which is a deep approach. We do variational autoencoders for collaborative filtering. And this is based on a more recent paper. It's from this year by some Netflix, Google, and MIT people. And the reason, we'll get into the details later, but the reason I did variational autoencoders was basically that I wanted to learn the method. So that's it. Let's start. Yeah.
Can you see from here the screen, or should we maybe move it a bit? Can you see the screen? Okay, perfect.
Cool. Yeah, so interrupt me with questions at any time. I mean, it's a study group, so as soon as you have things that you're wondering about, or suggestions, or pointing out remarks, whatever, just tell me. So we start with imports. And basically, the deep model will be built in PyTorch. Pandas for data handling. LightFM, that's the package from Lyst to do the factorization machine. And then with handling's a little bit of words. I do some NLTK stuff, date times, plotting in Matplotlib, Seaborn, NumPy to handle arrays, so on. So that's what we're going to need. And here is, so the original talk was based on a PowerPoint presentation, so I just copy-pasted some slides into this. But today, my recommender problem is that I want to recommend what these guys should write their next paper about. Based on their previous history of articles they have written. So that's my idea. And I apologize for only showing old men here, of course, but I wanted to have this sort of relatable, so you know these people. And since I wrote this, I have found some really, really, really talented female academics as well, but I didn't have time to put them in. So that's the problem. And now we're going to find data. So I found a GitHub package called Archive Scraper to download archive papers. Very easy to use. I had to modify this a little bit, the code, to get exactly what I wanted. So actually it's not completely reproducible here from the code, but maybe I will push the change I made so you can run it through. I will put the notebook online afterwards. But basically the idea is that you scrape all the articles that's on the archive. And I put it from the stat category. So you input stat and I put dates. So we'll do 10 years of papers and then start scraping. I will not execute the code in real time because it will take hours to run through the notebook. But basically we'll fetch the records by calling their open API. Blah, blah, blah. We go get all the records.
So did you download the full text or just
No, it's just the abstract and some metadata. We will look at the metadata. So yeah, the data looks like this. It's a JSON where you have the title, the ID, the abstract, categories, I mean the tags that they put the paper on. When it was created, some link to some journal information, the authors, and the URL to the paper. So that's how the data looks like. And I'm only going to use the title. So basically the items that they have in the recommender system, you have users and items, and my users are the professors or the authors of the papers, and my items are words in the title. So we split into a training and validation set. I take all the papers up to March this year as my training set, and then we'll validate on articles that has been written since then, or published since then. Right. And I want to, so this is basically unstructured data, of course. So now I want to parse it into a format I want to use. Yes.
Sorry, items are words in the
title.
So
Words in the title of the paper.
Single words.
Single words, exactly. So basically the idea is that if you have written about Bayesian, maybe you want to write about variational. Yeah, that's I mean, it's always fun. I have held a lot of meetup talks, and it's always fun to have a nice data set that people can relate and understand, and something that is freely available on the internet, and a little bit fun. Fun from a very nerdy perspective, of course.
But so these guys are basically the superstars, right? So they should, in our perspective, should they be quite similar in their take? Or is
we will actually, so if you know recommenders, you will have a vector representation of the authors in the end. And we can see how similar they are by taking the scalar product. We'll do that in the end. So basically parsing, and this is where I use the stop words. I don't want to have and I and what and so on. So I take the stop words from NLTK and I add some extra stop words that are basically common in stat papers, not contributing that much, but not in the stop words list. And I pull out the data in this parser code, stripping out some strange letters, strange characters, parsing the JSON. And I do this for the training and the validation set. So we won't have time to go into the details, of course, but basically, after the parsing, I get the training set that is 680,000 author title combinations in my training set, and then 100,000 basically in the validation set. And the split is 87% in the training set. And this is how the data looks like after I've parsed it. So I have generalized, Matai has written about generalized, together with how Bolt. So that's one paper, and they become different rows, because that's how Bolt we can thought of has purchased the item generalized. And then Matai has also written a paper, entropy is probably in the same paper. So we get all these combinations. So that's the beginning of my data set. We can look at how popular the categories are. So computer science is very popular. Math, physics, quantum biology, condensed matter physics, qualitative finance. So that's basically the most. So you have 39 categories of computer science papers. So if you know, we'll get into the details later, but if you know the recommender system, we also want to add features on top of the dataset, not just combinations of user items. Then we will have these categories to build features eventually. So we can solve the cold start problem. Yeah, so I just plotting this data to get a feeling of what's popular.
What is the unique tags here? Because you said you had, is that one word in the title, unique tag, the variable unique tags?
No, the tags are how I tag my paper. So if you go back to the paper, they are in categories: math, statistics, condensed matter, statistical mechanics. So those are the tags. I will use those to create features.
All right, I see.
Yes.
And you grouped them all into, so you didn't separate them. You took the.
No, I will separate them later. Okay. Yeah.
And if an author has multiple papers, how do you create the tags? How do you associate the tags to that author? You combine all of them, or?
Yeah, I made the outer products. They will be in all the different combinations they have. Right. So let's look at some plots. This is popularity of some words over these 10 years. For example, we can see the sharp rise of deep in the titles of archived papers since, surprisingly enough, only 2016. But people are slow on the train. Then we see clustering has been sort of constantly popular. Adversarial is our new upcomer, only since last year, going up fast here. So in recommenders you always have the problem of it's not a static problem in the time domain. So you need to catch trends in a good system. And here we can see that there's definitely trends. I mean, even professors are jumping on the latest trends.
Unrelated question. Did you actually look at why there's what the spikes are?
Yes. So
Are they like ICML or?
well, no, I haven't looked at the spikes. No, I guess that could be before big events. Absolutely, good guess. It could also be, I mean, a vacation. So usually it would come late in the spring or late in the autumn, probably like that, after a season of work. Yeah, so that's my data set. And now let's go into the technical details. So recommendation systems, let's do some equation here. So I have my xy is my vector of counts for all users, y is previous authors, tokens. And then I have the problem is basically to predict the likelihood of your next item in terms of in the space of all possible items I could choose next. When I go into Amazon, I look at the books they suggest me is basically estimated on my probability of choosing that book as my next item I want to purchase. So that's the conditional probability here, and it's conditioned on my previous purchase history, conditioned on some feature vector for me as a user or as a professor, as a feature vector of the item. And that's the most general formulation of the problem. And in collaborative filtering, that's basically I'm skipping the V and the W. So I skip the features and I only look at the click history. That's sort of the definition of collaborative filtering. In content-based, I do the opposite. I skip the click history and only look at the features. And if I have an approach where I combine them, it's called a hybrid approach. So in terms of the two papers we're going to discuss, the Lust Light FM version is looking at both features and the click histories, or the item histories. I will use the word click histories because that's what. But you can think of it as my history of tokens I have had in the articles I have written. Yes.
Can you explain what the vector x is exactly again? It's one dimension.
Yeah, one dimensional for each author exactly, where I have once or twice if I have written about an article once or twice. So it's just, the combination of, usually people put it as a matrix, where they have the users as columns and items as rows, and you have ones where they have an interaction.
But then you introduce time here also. Is that a different variable x you?
No, well, so because the time is of course very important in the system, because if I'm a movie recommender and I'm recommending Star Wars 2, and someone has watched Star Wars 2, maybe it doesn't make sense to recommend Star Wars 1, but we should look at Star Wars 3 instead. So just to get a feeling of that time is important in this dimension, but in this problem, but I will skip t here, actually. We'll do it static in time. So I skip the t in this
just
sort of SOP notation, sorry.
So users are the same as authors?
Yes.
And items are the same as
words in the title.
Words in the title, actually.
Yeah, exactly.
Do you use the number of words that author used as a possible implicit feedback on the authors?
Yes, exactly.
Is the feature W, is that time dependent?
In my case, it is time independent, exactly. But I mean, if you made, the next level would be to make it time dependent. So for example, in my split between my training and my validation set, I will fix the feature vector for my training set. And then in the validation, I will only use the fixed feature vector for. Right. So classical collaborative filtering is done with matrix factorization. I mean, that's one of the first things that people started doing a long time ago. And this is mathematically equivalent of finding embeddings of users and items into some space, Rk, I can call it my latent space. Some function f theta, where theta is the parameters I want to fit with my machine learning model. And then my estimation of the conditional distribution up here becomes the scalar product between the embedding of the user and the item. Sort of a mathematical formulation of the picture I try to draw here, where we have, this is the click matrix or my user item matrix, and my factorization becomes the embeddings of the users and the items. And when I try to recombine them into the original matrix, I get my predictions for items that are not in the original matrix. So back in the days, people used singular value decomposition for this, for example. But basically, we can see that Jan LeCun is a vector in this scenario, and he becomes embedded in my k-dimensional space. The same as clustering is a word, it becomes embedded in my k-dimensional space. And since I now have a representation of them as numbers in some space, I can take the scalar product. So it's important to note that in classical matrix factorization, if I had a perfect factorization, I wouldn't have gained anything, because when recombining the original matrix, I would just get what I started with. So the point is that it's not perfect, which is sort of interesting. So you try to optimize the imperfection.
Did you limit the vocabulary list? Usually in SVD, you kind of take the 10,000 top terms, or
no, I didn't. No.
You had a huge,
yeah, I have. It's a very sparse matrix. Yeah, we'll see that that becomes a problem later. So the generalization from classical collaborative filtering is do something is factorizing machines. I say factorizing machines, but it's actually factorization machines. And then you turn this into an equation where you also make embeddings of the features. So one feature, for example, could be my age. And I make an embedding of that into my feature space. And now I can take scalar product with that and the items, for example. So if you go back and look at this equation here, where you just take the scalar product, factorization machines are just a generalization where I now do embeddings of also my features. With some bias terms, of course, but that people usually do in classical matrix factorization as well when they do stochastic gradient descent and so on. But I'm skipping that part in the history of this field. And I can do activation function, like I do with the neural network. I have the option of choosing different activation functions when I calculate my conditional probability. But we will also only use the identity function. And now the set of embeddings, the set of my possible embeddings and now items, users, and features. And in the original paper, he added higher order interactions between the features and the items as well, but I will do it just with this scalar product here. And it's, as I said, it's the embeddings and the biases that we learn when we train. So basically, how we optimize on some metric so that we learn embeddings that can reproduce the item and the user as good as possible and predict with the scalar products. Ah, this one. Yeah, okay, because, right. Yeah, so maybe it's harder to see further down. Okay. Yes. So, that's the most general, that's the general formulation of the factorization machine. What the Lust guy, Maciel, if I'm saying that correctly, what he's doing in his paper is that he restricts that further by doing a weighted sum of user embeddings and a weighted sum of item embeddings, and then just taking the scalar product of the weighted sum of those vectors to make it easier to calculate. I mean, it sort of makes sense, I think, because if these vectors point in different directions in the space of embeddings, my latent space, adding them on top of each other doesn't lose that much information, actually, if they're fairly far from each other. Is that a problem with the door? Ah, okay.
Somebody went to check.
Okay. Sure. That's the theory. I mean, I expect you to have questions about this, so please ask me. Okay. So now I have the theory and I have my data set, so now I need to adjust my data set so that I can actually do, yeah, right. Y is my conditional probability that I want to estimate up here. Yes, right, I changed from P to Y. So that's basically my...
Is that the loss function, or is that what you want to optimize?
We want to get into that, but...
I guess Y is essentially a cell in that R
yeah,
matrix.
yes, exactly. Yes, exactly. But I can think of it, if I have the sigmoid as my activation function, I can think of it as the probability of the user choosing that item. But if I have a different activation function, I cannot interpret it as a probability anymore. Right.
Sorry, it's a conditional probability of what?
Of these three vectors.
Oh, okay.
So my features, my user features, my item features, and my item history, my paper history. Right.
So is it the case if you go to the equation for factorization machines that you can come back to the pure collaborative filtering if you just have one X non-zero for which
Yes.
item and
Yeah.
one X non-zero for which
So if I skip my feature embeddings, the machine sort of simplifies to the collaborative filtering case, the matrix factorization case.
And there are some of these X's that are which user and some of the X's which are which item, and then some other features
Yes.
as well.
Yes.
Okay.
So I mean, the idea is extremely simple. You just make embeddings of everything you have, and then when you have embeddings of them as vectors, even though it's an item or a user or my age, whatever, I can take the scalar products in my embedded space and then calculate if I do a sigmoid as my conditional probability. Right. Exactly. So now I group my interactions to get my click matrix, my user item matrix. You can group by token and author for the training and the validation set, and I can look, for example, how the data looks when it's grouped. Sorting on values, so we can see that Dunson has written about Bayesian 31 times. So that means basically that Dunson likes Bayesian a lot. Ayasha likes Monte a lot, and so on. And now I want to create the matrices that I can input into my model to actually train these factorization machines. And now I build this is my feature vectors, right. So I take, as features, I take how many times a user has written an article in a certain category, or how many times a certain word has shown up in a certain category. So let's say Bayesian shows up in people writing in stat category often use the word Bayesian, for example. That would be a feature on the word Bayesian. It says that this word is very common in the Bayesian category on the archive. So here I do some slow Python code and remove tags that are very uncommon, for example, to-dos here that I didn't fix. But basically you can see here that the word drought, in 13% of the papers where drought has been used, the paper was also added to the category stat.me. And this, right.
Can you just bring the page up? Yeah.
Okay, sorry. And this is basically a feature. Let's say so the analog here would be that I'm purchasing books on Amazon. And a feature about me is that I usually buy books in the sci-fi category. So that would be a feature about me that tells me something about what kind of person I am. Or the similar way, an item feature would be that Asimov's book, that's a sci-fi author, his books are usually purchased by older men, let's say. And that would be a feature on that item. And I can use that when I make recommendations, because if an older man comes into my online shop, I can say that, okay, let's recommend him items that are common in that category. Or in a similar way that as a sci-fi reader, they recommend me sci-fi books. That would be the analog here. Right. And the same way in user tags, Danilo Brzduk, 12.5% of his papers has shown up in the stats.machine learning category. And that would be a user feature. So now I have all the things that I need to make a hybrid recommender. I have the history where with my tags for this author has written about this subject, and now I have also the features that I want to add to that, into my factorization machine. And this makes this a hybrid approach. Yeah.
The problem that they're very sparse. Some
Yes.
categories have a lot of...
Yes. So this, and we'll scroll up now. So let's see this. Now I want to create the feature and user matrices. And now I skip all the combinations where the interaction is 0 to get rid of them. Because it's the factorization machine approach is encouraging sparse representation, or it handles a sparse representation. So actually I only need to keep the actual interactions that I actually have. And in Python that's represented by these sparse matrices.
So there you basically intersected your features, artificial features that you created to create another matrix, right? So you will have two matrices, one features intersection, artificial feature that you created, and one is history.
Yes, exactly.
Okay.
And you basically just concatenate them.
Okay.
So the way that this Python packages handles that is peculiar. It's not peculiar, that's definitely the wrong word, but he has a special method for that. But I will use some functions to create those matrices automatically.
So what do you mean by concatenating? Do you put them in one big matrix, or do you use the artificial matrix as a boost for collaborating different features choice?
So basically you can think of the click user matrix, that's the first matrix I have here.